So for this one, want to determine the Norton's equivalent circuit. To understand which one is your load resistor, in this case, it's this one here. Once you have determined which one is your load resistor, remember for Norton's circuit, we want to determine the Norton's current, IN. So we want to determine the Norton's current, IN. That will be connected in series with a resistor, Norton's resistance, and then connecting to the points A and B. Now, to do that, first we need I Norton. To get I Norton, we need to determine the I short circuit. So we come to where A and B are, where the load resistor is. We need to short it so that we find the short circuit current. So where we have the load resistor, which is there, we're going to replace with a short circuit. So now we need to find the current that will be flowing down that way. That will be the one that will be equal to I Norton. So for the circuit that we have now, we need to analyze to find I short circuit. So what will happen? Well, first let's understand what the short circuit there does. See, with the short circuit in place, one thing becomes obvious. This 5 kilo ohm resistor here will no longer be working, or the current will be bypassing that resistor. So no current will pass through this route. So this will basically be off. So the circuit will now look like this with the short circuit in place. So since that is how the circuit will look like, let's analyze it to determine what I short circuit will be. You quickly observe that it means that since this is a current source, the dependent current source, all the current from here comes to pass through here in that manner. And they'll have the same direction. So our I short circuit in this case will actually be equal to 0.01 V0. They have the same directions. This is applying this way. Maybe I should be going this way. Here to be going downwards like that way. So they have the same direction, so positive like that. So this becomes the first thing, first equation. But we need to know what V0 is. But where is V0? V0 is defined here. So let's come to this second part to determine what V0 is. So here again, we have a current source. If this was a voltage source, we would have used Kirchhoff's voltage law. By being a current source supplying 5 milliamps, we can determine voltage V0, because V0 is the voltage drop across this resistor. So to determine the voltage drop there, we use Ohm's law. Voltage is equal to current times resistance. The current passing is the same current being supplied here. So the current passing is 5 milliamps. The resistance being supplied or receiving that current is the 10 kilo ohms. So the milli and the kilo will oppose each other. So we only have 5 by 10, giving us 50. So V0 is 50 volts. This allows us to get I short circuit. Since I short circuit is 0.01 times V0, so V0 is 50. When you multiply with 0.01, we get 0.5 amps. Is that okay?
Yes, sir.
So this becomes our I short circuit. So once we have our I short circuit, next thing, we need to find the resistor. But to get the resistor here, it might be a little bit difficult, especially when you have dependent sources in place. So for this configuration, what we're going to do is we're going to use a trick. See, the two terms, the two quantities, I short circuit and V open circuit. Usually when you're determining circuit, you determine the V open circuit. When dealing with Norton's theorem, we use I short circuit. But the two are actually related. The relation is Ohm's law. The open circuit voltage is equals to the short circuit current multiplying R. Here R can be taken as R Norton. But whether you take it as R Norton or R Thevenin, it's the same thing. But basically, this is what you have. This is the connection. Meaning, for circuits where you're dealing with a dependent source, where it's difficult for you to get the Norton's resistance directly, we usually choose to first find the voltage. And since we already have the current, we can get the Norton's resistance by dividing the open circuit voltage by the short circuit current. This will allow us to get the resistance. What am I saying? What we'll do is we'll come back to this circuit, get the original one. To get I short circuit, we shorted the resistor, the load. Now we're going to get the open circuit voltage. So we're going to open the load. So the load is this. We're going to open it. So we have opened the load. Now we need to find the voltage across where the load was. So we need to find the voltage that would connect there. The open circuit. Now you have to observe that the voltage we are looking for, the open circuit voltage, it's actually the same as the voltage used by the 5 kilo ohm resistor. So if I can find what the 5 kilo ohm is using in this case, then I would have found my VOC. So we just need to know what the 5 kilo is using. So how are we going to do that? Well, in this case, notice that with this line empty here, knowing what the 5 kilo is using becomes easy because all this current will be going towards 5 kilo. So meaning the voltage VOC will now be equal to, so it will be equal to the current being supplied multiplying the resistance, which is that 5 kilo. So this is what we're going to have. Here again, we see that to finish up this, we need to know what V0 is. We can simplify this a little bit. This would be 50 V0. Two decimal places will kill off the 2 zeros there. So you have VOC is equals to this. Now, to find what V0 is, we come back to this circuit. See, even in the absence of the load, notice that nothing has changed this side. Nothing has been changed this side. So V0 will still be equals to 5 milli multiplying 10 kilo. And just like before, this will still be 50 volts. So V0 is to 50 volts. So V open circuit will be 50 multiplying 50. So we're getting 5 by 5 is 25 with the 2 zeros. Volts. So this is what we're getting as our V0, our V open circuit. So we can verify this. We opened the load. We're looking for the voltage across the 5 kilo, which is 5,000 ohms. So the current passing through 0.01 V0. That's the current passing times 5,000. And then that gave us 50 V0. And then 50 V0, we came back to find V0 for this part. V0 is the voltage across the 10 kilo, which is 5 milli by 10 kilo, which is 5 by 10, 50. So it's now 50 by 50. So yes, we do get that. Since we now have V open circuit, you can get R Norton, which will be V open circuit, which is 25, divided by I short circuit. I short circuit is 0.5. This will be 5,000 ohms or 5 kilo ohms. So we now have I Norton and R Norton. So our circuit then becomes I Norton 0.5 amps. And then this is 5 kilo ohms. And then our load is this side. What was our load resistor? Come back to the original circuit. We're done with the analysis. 20 kilo ohms. So here we have 20 kilo ohms as our load. What was the question? The question was to find what? To use Thevenin's equivalent circuit, which we have found, to find the load current, the current through that 20 kilo ohms. So we're finding current here. So we can use Kirchhoff's current law. Oh, no, not Kirchhoff's current division. Load current will be the other resistor, which is that 5 kilo over 5 kilo plus 20, multiplying the current they are sharing, which is 0.5 amps. So this will be 5 over 25 by 0.5. So this will just be 0.5 over 5 or 0.1 amps. So that is going to be the load current. Okay, any questions?